Graphs are a fundamental data structure used to represent relationships in various domains. Real-world graphs are globally sparse, yet contain numerous pockets of high edge density. Discovering these dense subgraphs is a crucial task with applications in social sciences, bioinformatics, cybersecurity, and more. The problem is typically formulated as an optimization problem, but in real-world applications, one seeks a large collection of dense subsets that cover a significant fraction of the input graph. The authors propose a new definition of regularly triangularic (RTR) families, which capture the notion of dense subgraphs with many triangles and comparable degrees. They design a provable algorithm, RTR extractor, to discover RTR families that approximately cover any RTR set. RTR extractor is efficient and inspired by recent results using triangle counts for community testing and clustering. It achieves high coverage on real-world datasets, for example, covering a quarter of the vertices with subgraphs of edge density more than 0.5 for datasets with 10m plus edges. The algorithm's utility is demonstrated for unsupervised graph discovery tasks, showing correlation with meaningful sets of similar vertices in a citation network. RTR extractor has significant implications for various applications, including finding cohesive social groups, spam link farms in web graphs, graph visualization, and more. The paper introduces a novel approach to dense subgraph discovery, focusing on triangularic sets and their practical applications in machine learning and data mining. It defines regularly triangularic (RTR) sets as subsets of vertices with comparable degrees that contain many triangles, providing strong theoretical guarantees for algorithms and guiding practical dense subgraph discovery. The authors designed the RTR extractor algorithm, which outputs a disjoint family of RTR sets, with a strong recovery guarantee showing a constant fraction of every RTR set is contained in the family. Under certain conditions, a constant fraction of the set is contained in a single output of RTR extractor. The algorithm's design incorporates tools from theoretical work on triangle-dense decompositions of graphs. A fast implementation of RTR extractor is also provided, incorporating heuristics to improve coverage. Experiments on large real-world datasets demonstrate RTR extractor's efficiency and effectiveness in finding dense subgraphs, significantly outperforming existing algorithms in terms of coverage and scalability. The authors introduce a novel method, RTR extractor, for covering graphs with dense subgraph families using triangularic sets. This approach outperforms state-of-the-art dense subgraph discovery algorithms and community detection procedures in various datasets. RTR extractor consistently identifies numerous large, dense sets and graphs, often with mean edge densities exceeding 0.8. It also demonstrates semantic significance by grouping similar vertices in labeled networks without prior knowledge of the labels. The authors discuss related work in dense subgraph discovery, community detection, and triangle-based methods, highlighting the importance of finding many large dense subgraphs and the limitations of existing algorithms. They formulate the main problem as finding many sets that are dense in a graph, pointing out the limitations of traditional notions of density such as edge density and average degree. Instead, they propose a more nuanced definition of density that accounts for the degrees of the vertices involved. They introduce the concept of regularly triangularic sets, combining triangle density with edge density to capture the desired properties of dense subgraphs. Triangle density is defined as the number of triangles in a set divided by the number of possible triangles, which forms the basis of their algorithm. Overall, the authors present a novel approach to dense subgraph discovery that leverages triangularic sets to find numerous large, dense subgraphs and graphs. Their method outperforms existing algorithms and provides a more nuanced understanding of graph density. In the context of graph theory, an alpha regularly triangularic set is defined as a set of vertices with total degrees ranging from alpha s to s alpha and a triangle density of at least alpha. The significance of this concept is demonstrated through its application in the RTR extractor algorithm, which outputs a family of disjoint sets, each being omega-1 regularly triangularic. Notably, every omega-1 regularly triangularic set has a constant fraction of its vertices in the output T. A beta well-separated alpha regularly triangularic set is further defined, requiring that for all edges containing at least one vertex in the set, the edge contains at most beta s triangles where the third vertex is outside the set. For any well-separated regularly triangularic set S, there exists an output set T that contains a constant fraction of S. This concept is crucial in establishing a connection to coverage, as a large portion of the graph G can be covered by disjoint omega 1 regularly triangularic sets, implying that a constant fraction of each of these sets is present in the output of RTR extractor, thereby ensuring good coverage. The RTR extractor algorithm is inspired by theoretical decomposition results by Gupta, Roughgarden, and Seshadhri. It operates by using triangles to guide the local extraction of a dense cluster, and iteratively deletes edges and vertices based on certain conditions, eventually outputting a family of disjoint sets. The algorithm's utility is demonstrated through its ability to weakly discover all omega 1 regularly triangularic sets in a graph, providing a strong guarantee for coverage. The RTR extractor algorithm is a groundbreaking method for identifying and extracting dense subgraph families from a given graph, focusing on triangularic sets. It iterates through a cleaning process and extraction steps to ensure that the output sets are regularly triangularic. The cleaning step removes edges participating in too few triangles, while the extraction step finds vertices in the two-hop neighborhood that form many triangles with the neighborhood. The analysis of RTR extractor consists of two parts, proving that the output sets are regularly triangularic and showing that a given regularly triangularic set is approximately captured. The tension between these goals arises due to the need for aggressive cleaning to maintain triangle density and the requirement to preserve an existing triangularic set. The analysis resolves this tension by utilizing an accounting in terms of triangles, which proves more powerful than tracking edges and density. The regularly triangularic definition ensures a core of the set remains intact during deletions, and the well-separated condition prevents significant fractions of the set from being removed. This leads to the conclusion that every set output by RTR extractor is omega 1 regularly triangularic, with practical parameters set as constants. The authors continue to explore the properties of the RTR extractor algorithm, focusing on the regularity and triangle richness of the extracted sets. They prove that the output of RTR extractor is omega 1 regularly triangularic, with a constant fraction of every omega 1 regularly triangularic set contained in the output. This is achieved through a series of lemmas establishing bounds on the number of triangles and degrees of vertices in the output sets. Specifically, they demonstrate that for any vertex in the output, its degree is within a constant factor of the maximum degree, and the number of triangles is at least a constant fraction of the cube of the maximum degree. The authors then analyze the process of vertex deletions and extractions, showing that there exists a setting of epsilon and beta as poly alpha, such that an omega poly alpha fraction of vertices of S is present in the family T. This is encapsulated in lemma 5.2, providing a lower bound on the number of vertices from S that end up in output clusters. The analysis involves a careful examination of how vertices in S get deleted from the current subgraph H and the role of the parameter beta in the extraction process. The results have implications for the study of social networks and other real-world graphs, where these properties are indicative of community structure and cohesion. The concept of a graph with dense subgraph families is central to understanding the algorithm's approach. Specifically, it involves triangularic sets, where the algorithm's efficiency is enhanced by the Chiba-Nishizaki algorithm for triangle enumeration. The algorithm's handling of vertices in set S or its neighborhood is crucial, as is its ability to remove vertices from S when applied to real networks. Heuristics such as the growing heuristic and parameter choices like epsilon can significantly improve empirical performance. The datasets employed in the evaluation of RTR extractor are a crucial aspect of the research. The algorithm's efficiency in terms of storage and running time is particularly noteworthy, thanks to the triangle recomputation trick. Experimental results demonstrate RTR extractor's superiority in coverage at high densities compared to other state-of-the-art procedures. Additionally, the summary addresses limitations in future work, emphasizing the need for further optimization and the exploration of new algorithms. The research paper examines the performance of algorithms in identifying dense subgraphs within networks, focusing on RTR extractor, Louvain, and K-truss methods. A comparison with greedy and flowless algorithms is also presented across 11 datasets at two density thresholds, 0.5 and 0.8. The results indicate that RTR extractor and Louvain outperform other methods in terms of coverage, with RTR extractor showing a significant advantage at the higher density threshold of 0.8. RTR extractor consistently exhibits high coverage across different thresholds, while competing methods experience sharp drops in coverage as the threshold increases. Regarding the largest output sets, RTR extractor produces smaller, denser clusters with densities often exceeding 0.9, whereas greedy, flowless, and Louvain output larger and sparser clusters, particularly in larger datasets. The paper presents a quantitative evaluation of the output sets, highlighting RTR extractor's efficiency and effectiveness in identifying dense subgraphs, making it a preferred choice for this purpose. The RTR extractor algorithm has been evaluated for its effectiveness in identifying clusters within a citation network. This evaluation demonstrates the algorithm's ability to extract clusters from a large-scale dataset comprising 660,000 vertices and 3 million edges, obtained from sources such as DBLP, ACM, and the Microsoft Academic Graph. Two specific clusters are highlighted, one focusing on spatial joins with an edge density of 0.96, and another centered around object-oriented programming, particularly traits, with an edge density of 0.58. These clusters consist of papers published in similar venues over a decade, illustrating the algorithm's ability to identify meaningful subnetworks without any prior knowledge of semantic features. Visual descriptions of these sets are provided using Fruchterman-Reingold drawings, which illustrate the structure and connectivity within the clusters. This visualization underscores the potential of RTR extractor for unsupervised knowledge discovery in citation networks. The paper also emphasizes the limitations of traditional greedy algorithms that aim to maximize average degree, as they tend to favor large subgraphs with low edge density over smaller, denser subgraphs. In contrast, RTR extractor is designed to optimize for edge density, making it more suitable for identifying densely connected sub-networks within complex networks. In conclusion, the RTR extractor algorithm is efficient and effective in identifying meaningful clusters in citation networks, particularly in the context of computer science research. Its ability to extract densely connected sub-networks, coupled with its unsupervised nature, makes it a valuable tool for researchers seeking to uncover hidden patterns and relationships within large datasets. The authors present visualizations of subgraphs extracted by the RTR extractor algorithm, showcasing its effectiveness in identifying densely connected vertices. Figure 3 illustrates two subgraphs, one from Table 5 and the other from Table 6, with vertices arranged by closeness centrality. The lowest degree vertex is denoted by a triangle, and the red vertices form the extracted cluster. The blue and green vertices belong to other non-trivial clusters. The authors note that the cluster vertices are much closer to the central vertex in terms of closeness centrality. The authors then discuss what is excluded from the sets, examining the set of papers in the neighborhood of the first vertices that are not included in the output sets. They find that the excluded vertices are indeed irrelevant to the set as a whole, with most of them having low induced degree or participating in other clusters. The authors conclude by presenting the RTR extractor algorithm and its success in efficiently extracting sets of densely connected vertices by leveraging triangularic sets. They propose future research directions, including generalizing the cleaning procedure as a sparsification method for various downstream tasks and exploring ways to organize the output sets of RTR extractor to give a hierarchy of clusters. In the realm of network science, dense subgraph detection and community structure have been a focal point for numerous research papers. A spectral theorem on cluster structure in real-world graphs serves as a foundation, shedding light on the inherent organization of complex networks. This is followed by studies on cohesion and performance in groups, which explore how densely connected subgroups contribute to overall network efficiency. Higher-order organization of complex networks is another key area of investigation, highlighting the intricate patterns that emerge when examining networks beyond simple pairwise connections. Fast unfolding of communities, a method for identifying densely connected clusters within large networks, has also garnered significant attention due to its potential applications in fields such as social network analysis and biological systems. The detection of densest K-connected subgraphs, a problem aimed at identifying the most densely connected sub-networks within a larger network, has been extensively studied. Similarly, flowless subgraph extraction, a technique used to identify subgraphs with minimal flow between them, offers insights into the compartmentalization of networks. Large-scale density-friendly graph decomposition, meanwhile, provides a framework for breaking down massive networks into smaller, more manageable components based on their density. Research on triangle-dense graphs, which are characterized by an abundance of triangles, continues to advance our understanding of network topology and its implications for network behavior. Graph clustering, a broad term encompassing various methods for grouping nodes based on their connectivity, has been applied in diverse contexts including computer vision and bioinformatics. Community search over big graphs, a technique designed to identify communities within large networks, further underscores the importance of understanding network structure at multiple scales. Finally, a comprehensive survey on the densest subgraph problem and its variants provides a thorough overview of the challenges and opportunities in this burgeoning field. By delving into these research papers, we gain a deeper understanding of the intricate patterns that underlie complex networks and the tools necessary to unravel them. The authors expand on previous research in dense subgraph discovery, drawing from influential works such as Huang et al.'s 66, triangulation-based dense neighborhood graph discovery and Xu et al.'s 67, efficient algorithms for generalized densest subgraph discovery. They also connect their approach to weighted gene co-expression network analysis, as introduced by Zhang and Horvath, 68. Their proposed method focuses on covering a graph with dense subgraph families, utilizing triangularic sets to enhance efficiency and effectiveness. This approach is based on the concept of dense subgraphs, which are subgraphs with high edge densities. By identifying these dense regions, the authors aim to uncover underlying patterns and structures within the graph. A key component of this approach is the use of triangularic sets, which are sets of nodes with high triangle densities. These sets act as a proxy for dense subgraphs, enabling the authors to develop efficient algorithms for dense subgraph discovery. The incorporation of triangularic sets allows for a more nuanced exploration of graph structure, capturing subtle patterns that may be obscured by traditional dense subgraph discovery methods. The author's contribution is twofold. Firstly, they provide a novel framework for covering a graph with dense subgraph families, applicable to various domains including social network analysis and bioinformatics. Secondly, they demonstrate the efficacy of their approach through a series of experiments, showcasing its ability to uncover meaningful patterns and structures within graphs. The mathematical foundations of this approach are rooted in graph theory and combinatorial optimization. The authors employ techniques from these domains to develop algorithms that efficiently identify triangularic sets and subsequently construct dense subgraph families. The resulting framework is scalable and efficient, making it suitable for large-scale graph analysis. In terms of limitations, the authors acknowledge that their approach relies on the assumption that dense subgraphs are indicative of meaningful patterns and structures within the graph. Future work may involve exploring alternative methodologies that can capture more nuanced graph properties. Nonetheless, the author's contribution represents a significant advance in the field of dense subgraph discovery, offering a powerful tool for graph analysis and pattern detection.